So I'm going to discuss the tangential and normal component of acceleration. When we want to describe the motion of a particle which is moving along the curve, so we have the speed, we have the velocity, we have the acceleration. We have discussed all of that one. Then we have taken the unit tangent vector, that is the motion tangential to the line of the motion. So the particle is moving and its velocity is changing, it means acceleration is changing. When acceleration is changing, it has the component of accelerations. So obviously the components, one is along the tangent line, tangent to the curve, and we have discussed unit tangent vector as t of t. Another one, we take the other component is normal to that one. Normal to tangent, we discussed the component of the principal normal vector. So we have two components of the acceleration. One is tangential to the line and the other is normal to the line. So we can distribute our vector A along the tangent to the line and normal to the line. We look on this curve that we are having point P, and at point P we have the unit tangent vector and we have the principal normal vector. So this is my vector A, the acceleration vector. So if the component along the unit tangent vector along the curve, this is my curve with curve C. So then we are having here, this is a n at t, and we take at, that's the value of the unit tangent vector, value of the component of the acceleration. So this is my n, and we have an, this is the normal component of the acceleration. So we can, as I told you, we can write this A is equal to at of t and plus an, this is the component of normal vector nt. So we can write this value of, we're having the function r, this is describes this function r, the vector value function is equal to f of ti, that's describing the curve, g of t j and h of t is equal to a square is equal to, this is our right angle triangle. So get here, this is a t whole square plus a n whole square. As we describe, these are perpendicular each other. This component, this n and this t, is the unit vector. We have said this is here n dot t, this is equal to 0, and we have seen also here they are orthogonal to each other. So we can write as when we find the value of at, we can find the value of an by using this one when we have the value of a. But here we have the formulas for finding the unit tangent vector, the component of tangent vector and of acceleration. So the tangential component we can write in terms of our r of t, then we denote by a t is equal to r dash of t dot r double dash of t over r dash of t magnitude of this one. And from there we can also find the normal component of acceleration. Normal component of acceleration we can find by using the Pythagoras theorem, or we can just find them directly. This is where an is equal to, here we get the cross product. We have r dash of t cross r double dash of t, we take the magnitude of this one and divide by the magnitude of r dash of t. So we can write this also, we can have other formula for that. We can just write here an, we can write this is equal to, as I told, this is where an is equal to under the root of a whole square minus a t whole square. So we can use this one and find an. So the third thing we want to find, we can use also this one to finding the curvature of the curve by using the formulas. So that's very also, we can have the derivation of this one, we can find, we have already given few formula for that one. This is another formula. The curvature is equal to r dash of t cross r double dash of t over r dash of t whole square, the whole cube. That gives the curvature. This I can also take as an, and this one, and we can write this is our 1 over r dash of t whole square. If I have my an, I just divide by this one, and that give me the value of curvature. So this we can use this an for finding the value of curvature, because obviously here you can see for finding an we have the using cross product, and if we can want to make sure, that's also correct that you use the Pythagoras theorem and we have, once you have a t, and in a t you need the dot product. So I'm not going to have the derivation. You can find in the calculus book the derivation of these all formulas very easily. Simply we take the derivatives and simplify this one from the velocity, and we can derive these formulas. So I give you an example and explain you the application of the formula for finding the tangential and normal component of acceleration. I'm going to give you an example that we have a particle that's moving along a curve, and the curve is being described by the position vector r of t, and that's equal to 3ti plus t squared j plus 3t squared k. Want to find along this curve at any time t the curvature of the curve. Also we find the vectors we see the motion, and we can find the component of acceleration, tangential component, also the normal component. So we are having this example solution of this one. We will use our formula that we described for finding the acceleration component. We need r dash, r double dash. We find r dash dot r double dash, the dot product, r dash cross r double dash, the cross product. In this example, you can see we have the whole knowledge we have discussed in the vectors and vector value function, taking the dot product, cross product. All of this knowledge is being used in this example. So this is very important from examination point of view, because the examiner putting this question is going to check you for all the aspects which is being taught in this chapter. So we have here r of t is equal to 3ti plus t squared j, and now we're having here, t cube j, we're having here 3 t cube j, and plus 3 t squared k. Find r dash of t, I need it, r dash of t, that we say our velocity, 3i plus 3t squared j plus 6tk, the first derivative. Then we have r double dash of t. R double dash of t is our second derivative. We have here 0i because of constant, the derivative is 0. Plus we are having 6tj, and then we are having here 6k, because derivative of 6t is equal to 6. So we can find this one. Now as you have seen, we need the dot product. So we have the vector value function. For the vector function, we can find the dot product, cross product also. So dot product is r dash of t dot r double dash of t. This is equal to 3 multiplied by 0 plus 3t square multiplied by 6t, then plus 6t into 6. Simplify this one. Get here 0 and get here 18t cube plus 36t. So this is my r dash into r double dash. Now I am going to find the cross product. I find all the required values, and then I substitute the formulas and I can find the result. For cross product, we get here I, j, and k. My r dash is 3t square, 60, and my r double dash is 0, 60, the derivatives, into 6. And I simply find my cross product. This I into component of this one. This component is 18t square minus 36t square I. Then minus j, we are having is 618 minus 0j. Then with k, we are having 18t minus 0k. So we simplify this one. We can write this is, we're going to get the value is minus 18t square I minus 18j plus 18tk. So this is the cross product of my functions. Now here I need two more values. When I need here r dash magnitude, because I'm dividing by the magnitude of this one. The magnitude of r dash is our a1 square, a2 square is my vector r dash, and that give me here 9 plus 9t to the power 4, t square t to the power 4 plus 36 t square. I take 9 common, there become 3, and I'll get here this equal to 1 plus t to the power 4 plus 4 t square. Just writing in a proper way, we can write 3 into root of 1 plus 4 t square plus t to the power 4. So this is one thing which I need. Second thing, I need the magnitude of this r dash of t cross r double dash of t. I need the magnitude of this one. So I might find the magnitude of this vector. This is equal to 18 square, 18 square, 18 square. We can just write like this one. We are having 18 square minus 18 whole square, then plus minus 18 t square here. It's only again this here t square. So we take here t to the power 4, t to the power 4, and then here 18, simply 18 whole square plus 18 t whole square. So I can just change this one. This is 18 t square whole square because square is outside. So we can just say here inside we can take. Now I take 18 common. That comes out. 18 square becomes 18. And then here we come here t to the power 4. Get 1 and here we get t square. I just make the arrangement. I can write here 18, and the root sign we get here 1 plus t square plus t to power 4. So we have just calculated the dot product and we have to calculate the cross product. Now we can apply a formula. Number one, we want to find the tangential component of acceleration and component of acceleration, and that's my a of t, and we can write here this a of t is equal to r dash of t dot r double dash of t over r dash of t. Measure this one. I've just calculated all the values. I just find I have put the formula. We have r dash into r double dash. Just we have calculated this one, and the dot product is equal to 18t cube minus 36 squared. This is my here result. I think 18t cube is equal to 18t cube plus we are having here plus 36t. 36 over r dash of t we have just calculated, say 3 into under root sine 1 plus 4 t square plus t to power 4. We can just simplify this one, and we having here we take 18 common, we get here this is equal to 6 outside, and we get here t cube plus here we take 18 outside, we get here 2t over 3 is cancelled with this 18, and we have just cancelled that one, and this become here 6, and under root sign of 1 plus 4 t square plus t to power 4. This is my result for tangential component. Now I write here the normal component of acceleration. These are all examples we can just calculate by this way, that we are given the vector value function, and with the vector value function we find the first and second derivatives, and then as we need in the formula the cross product and the dot product to find the cross product and dot product r double dash, and then we take the magnitude of r dash and r cross product, and then simply substituting as we have the formula we are having here 18 into root of we have 1 plus t square plus t to power 4, and here we having the formula for r dash, that is here r dash we have just calculated here magnitude of r dash, that's here we having 3 over as we applied here also 3 under the root of 1 plus 4 t square plus t to power 4. 3 and 8 are cancelled, we get here 6. We can write here the common root, we get 1 plus t square plus t to power 4 or 1 plus 4 t square plus t to power 4. I hope you remember this one. We have root of a over root of b. We can write here under root of a over b. We given here root of a into root of b. We can just take the common one ab under the root. So this is allowed. We can solve this one. So this is the idea that we can find the curvature, the normal component acceleration, and tangential component. Similarly, we have the formula to find the curvature of the function, and we can apply our results we have calculated, or kappa is equal to r dash of t cross r double dash of t over r dash of t power 3. So we just make the substitution here. We having here r dash of t r dash of t or kappa is equal to 18 into root of 1 plus t square plus t to power 4. Now we take cube of this one. Cube of 3 is 27. 3 into 3 into 3, 27, and we get here 1 plus 4 t square plus t to power 4, and here under the root that's become, when we take cube of that one, then we can just rewrite it, and we can write this our value as 3 by 2, 4, and here we get 3 by 2. Now simplify this one, these are being cancelled and simplified, so we get here 2 by 3, 2 by 3. Here we can combine that one because we are having here the roots 1 plus t square plus t to power 4, and under the root sign we are having here 1 plus 4t square plus t to power 4. We can write like this one also. We write here cube. So that's my results, that we can find the tangential component, normal component of acceleration of a vectorial function r of t. This example we can expand it and we can write different type of RFTs. Obviously, we have before we have discussed this unit tangent vector, we have discussed velocity, we have discussed acceleration, we discussed speed for the vectorial function, and here today we are discussing the acceleration and the component of acceleration. I'll give you one more example.